Good morning dear students, this is Banani Porakayastha. I welcome you all to today's video. Here we are doing the chapter Matrices. So today we will start transpose of a matrix. So here we are starting transpose of a matrix and it is in page number 83. So before going to the definition, let us see the example given here. Here it is written if a matrix is given and this matrix is of order 3 by 2, then A dash means it is A transpose. A transpose can be written as A to the power capital T and we can write it as A dash. So A transpose will be the matrix whenever we will change this column into rows and this column also into rows. That means the rows will become the column and the columns will become the rows. So here you see the order of the matrix A was 3 by 2 and whenever we have done the transpose of A, the order of the matrix will become 2 by 3. That means the number of rows here is the number of columns of A transpose and the number of columns of A is the number of rows of A transpose. That now we go to the definition. So in definition 3 it is given that if A be an m by n matrix, then the matrix obtained by interchanging the rows and columns of A is called transpose of A. So the transpose of A is denoted by A dash or A to the power capital T. So this is the definition of the transpose of a matrix. Let us see the properties of transpose of matrices. Now what are the properties given? There are 4 properties of transpose of matrices. The first property is A transpose whole transpose is equal to A. So I am taking an example to check the first property. So let us take A is equal to 1, 2, 3, 4, 5, 6. So it is a 2 by 3 matrix. If we find A transpose, then it will be 1, 2, 3, 4, 5, 6. The first row will become the first column and the second row will become the second column. If we again find A transpose whole transpose, then it will again become 1, 2, 3, 4, 5, 6. So it was the matrix of order 3 by 2 and it will again become 2 by 3. So this is called A transpose whole transpose. Now you see, if the matrix A was A 2 by 3 matrix, A transpose was 3 by 2 matrix and A transpose whole transpose is again a 2 by 3 matrix. So from here it is proved that A transpose whole transpose is equal to A. The next property is Ka whole transpose is equal to Ka transpose, where K is any constant. Property number 3 is A plus B whole transpose is equal to A transpose plus B transpose. Property 4 is AB whole transpose is equal to B transpose into A transpose. So it is very important. Whenever AB whole transpose is given, it will be equal to B transpose into A transpose. Now we will start the example 20. In example 20, here 2 matrices are given and verify that A transpose whole transpose is equal to A A plus B whole transpose is equal to A transpose plus B transpose, and KB whole transpose is equal to KB transpose, where K is any constant. So let us move to the solution of example 20. So here it is the solution. Here matrix A is given, then A transpose will be, this first row will become the first column and the second row will become the second column. Again, if we find A transpose whole transpose, then again the first column will become the first row and the second column will become the second row. So A transpose whole transpose is equal to A. Next we have to do A plus B whole transpose is equal to A transpose plus B transpose. So for that, first of all we have to find A plus B. So whenever we add two matrices, we have to know that the two matrices should be of same order. So here both the matrices are of order 2 by 3. Now here we have to add the corresponding elements. So here it is the matrix A plus B. Now A plus B whole transpose means the first row will become the first column and the second row will become the second column. Now individually we have to find A transpose and B transpose. So see here, in case of A, the first row will become the first column in A transpose and the second row of A will become the second column of A transpose. In the same way, B transpose also we can find. So here it is the B transpose. Now we have to add A transpose plus B transpose. So here also both the matrices are of same order 3 by 2. If we add A transpose plus B transpose, then we have to add the corresponding elements of A transpose and B transpose. So here it is A transpose plus B transpose. Now from here we can say that A plus B whole transpose is equal to A transpose plus B transpose. Now we have to show KB whole transpose is equal to KB transpose. So for that we have to multiply the matrix B by the scalar K. So whenever we multiply a matrix by a scalar, each element of the matrix will be multiplied by that scalar. So here each element of B is multiplied by K, where K is the scalar. So here it is the matrix KB. Now we have to find the transpose of KB. Here the first row will become the first column and the second row will become the second column. Now we will take again K common and we will take it outside. So here it is KB transpose. So this is example 20. Now we move to example 21. In example 21 it is given that if matrix A is a column matrix is given, and matrix B is a row matrix is given, verify that AB whole transpose is equal to B transpose into A transpose. So for that we have to first multiply A and B. AB we have to find. So here is the multiplication. So since A is a 3 by 1 matrix and B is a 1 by 3 matrix, so the matrix AB will be of order 3 by 3. So you know how to multiply two matrices. Now we will find transpose of A. Since A is a column matrix, the transpose of A will be the row matrix. And since B is a row matrix, the transpose of B will be a column matrix. So here in matrix B, you see only one row is there. So in transpose of B, that row will become the column. After that, we have to multiply transpose of B into transpose of A. So you know how to do the multiplication. So here is the multiplication. Now you see the matrix we have from B transpose A transpose is same as AB whole transpose. So AB whole transpose is equal to B transpose into A transpose. So this is the solution of example 21. Now we will learn what is symmetric and skew symmetric matrices. So first one is symmetric matrix. So in definition 4, it is given that A square matrix. So remember that the line starts with the word square matrix. So whatever we will learn here for this definition, the matrix should be a square matrix. That means number of rows is equal to the number of columns. So let us read the definition. A square matrix A is said to be symmetric if A transpose is equal to A. Let us see the example given here. So here a matrix A is given. This matrix is of order 3 by 3 and clearly it is a square matrix. Now if we find transpose of A, then this first row will become the first column here. So this is the first column. The second row will become the second column here. So 2 minus 1.5 minus 1. The third row will become the third column. So 3 minus 1, 1. Now if we check these two matrices, then we will see that the two matrices are same. That means the order of both the matrices are same and it is 3 by 3 and the corresponding elements are also equal. So this is called the symmetric matrices. The next definition is skew symmetric matrix. Now here also the line starts with a square matrix. So whenever we will learn symmetric matrix and skew symmetric matrix, we have to know that these matrices are dealing with the square matrix. If a matrix is not a square matrix, then it cannot be symmetric matrix and it cannot be skew symmetric matrix. So let us read the definition 5. A square matrix A is said to be skew symmetric matrix if A transpose is equal to minus A. A square matrix A is a skew symmetric matrix if A transpose is equal to minus A. Here we have written A is equal to within the matrix Aij and A transpose is equal to within the matrix Aji. So let us take an example. Suppose A is a matrix of order 2 by 2. As the matrix should be a square matrix, then A transpose will be now see here these two. In matrix A, 2 is the element of first row second column, but in A transpose 2 is the element of second row first column. So here in A, 2 represents A 1 2, but in A transpose this 2 represents A 2 1. That is why we have written A is equal to Aij and A transpose is equal to Aji. Now since A was 1, 2, 3, 4, then minus A will be minus 1, minus 2, minus 3, minus 4. Minus A means the matrix A is multiplied by minus 1. So each element of A will be multiplied by minus 1. So minus A will become like this. So here also you see here these two in matrix A, 2 is the element of first row second column, and the element of first row second column in minus A, it is minus 2. So here 2 is A 1 2 and here A12 is minus 2. So A12 is equal to minus A12. So if A is represented by Aij, then minus A will be represented by minus Aij. Now if I is equal to j, then if we put I in place of j, then from here we will get Aii is equal to 0. Aii means the diagonal elements. I equal to j means if we are talking about first row, then we have to talk about the first column. If we are taking the second row, we have to take the second column. Since here I represents the rows and j represents the columns, in place of I also we can put this j, then we will get Ajj is equal to 0. This is also same as Aii is equal to 0. That means if suppose A is the matrix of order 3 by 3 and A is a skew symmetric matrix, then A11, A22 and A33, these 3 elements will be equal to 0. So here I have written, for example, B is a skew symmetric matrix of order 3 by 3, then B11, B22 and B33 are equal to 0. Here the elements of B are represented by small b. This is the example of skew symmetric matrix, matrix B. Here you see the diagonal elements are 0. So let us write one more example of skew symmetric matrix. Suppose I am taking matrix C. Then first of all what we need to do, we need to write the diagonal elements which are equal to 0. Now we have to write the non-diagonal elements. So I am writing here 1, 2 and 3. Since I am writing here 1, 2 and 3, I have to write it here minus 1, minus 2 and minus 3. Now you compare this C with this B, how they have written E, F, G and here they have written minus E, minus F, minus G. In the same way I have also written matrix C. Now you can check yourself this C is skew symmetric or not. So this is the definition of skew symmetric matrix. Let us come to exercise 3.3, and in exercise 3.3 the first question is find the transpose of each of the following matrices. So you can do this question. Question number 2, if matrix A is given, matrix B is given, then verify these two. This A minus B whole transpose is equal to A transpose minus B transpose is also same as A plus B whole transpose is equal to A transpose plus B transpose. for this question number Roman 2 of question number 2, you have to first find A minus B, then you have to find A minus B whole transpose, then you have to find A transpose, B transpose. After that you have to subtract B transpose from A transpose. Subtraction of matrices you know how to do. This is almost same as example 20. Question number 2 and question number 3 are same type of questions, so try to do also question number 3. Now question number 4, if A transpose is given and B is given, then find A plus 2B whole transpose. So for that you have to first find A, and A will be minus 2, 3, 1, 2. Now you have to find 2B. 2B means each element of B will be multiplied by these 2. Then you have to add A plus twice B. After that you have to take its transpose. So this is question number 4. Try to do question number 4. Question number 5 also same as example 21. And here two matrices are given for each question, and you have to verify AB whole transpose is equal to B transpose into A transpose. So for that, first of all you have to find AB, then you have to find A transpose, B transpose, then you have to again find B transpose into A transpose. So try to do up to question number 5. So with this I am ending today's video.